Hello, calculus students and general seekers of truth. Let's look at some theoretical implications of Taylor polynomials. And before we dive into that, let's look at a theoretical concept, I, which is defined as the square root of -1. So we want to find I squared. Well, I squared is just the square root of -1 squared, which is -1. I cubed is the square root of, well, maybe I can write it this way better, is I squared times I, which is -1 times I, or negative I. I to the fourth power is I squared times I squared, or -1 times -1, so that's just 1. And then I to the fifth is I to the fourth times I, so we're back to the original again. So you kind of have this loop here. I, if you square it, it becomes -1. If you take that and multiply by I again, you're going to get -I. And if you take that and multiply by I again, you're going to get 1. And if you multiply that by I again, you're going to get I. So this kind of ongoing loop forever. So no matter what power of I you have, it's always one of these four answers. So now I'm going to show you what Euler's formula is and where exactly it comes from. So remember that e to some exponent, so keep in mind that e to some exponent is equal to 1 plus the result over 1 factorial plus this blank here squared over 2 factorial plus the blank over 3 factorial plus the blank to the fourth over 4 factorial plus the blank to the fifth over 5 factorial plus that result to the 6 factorial plus that result to the 7th over 7 factorial plus the result to the 8 over 8 factorial, and so on, Okay? But that's enough now for us to work with and put the values in there. So let's put Ix in here, right? Since this is e to the Ix. And you might be wondering, well, what the heck does an imaginary exponent really mean? Well, I'm going to show you. So we put Ix into all of these, and let's see what happens. My pen is running out of ink here. Let's see. We put Ix into all of those, and so on. Okay, and then let's do the simplification. So this is 1. This is just simply Ix. This is going to be I squared x squared, but I squared is -1, so you're going to have -x squared over 2 factorial. This is I to the third, x to the third, but I to the third is -I. X to the third over 3 factorial. I to the fourth is just 1, so this is just x to the fourth over 4 factorial. I to the fifth is I again, so this is I x to the fifth over 5 factorial. I to the sixth is the same thing as I squared, so that's going to be -1. So that's -x to the 6th over 6 factorial, plus I to the 7th is the same thing as I to the 3rd, so that's going to be -I. X to the 7th over 7 factorial. And finally, I to the 8th is going to be the same thing as I to the 4th, which is 1. So that's x to the 8th over 8 factorial plus ... a bunch of other terms. Okay. So now, what I'm going to do is isolate the imaginary parts from the real parts. Okay. So if we consider the real parts, we have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and a bunch of other terms. And then here we're going to have I, and I'm going to factor out the I as well, so this is going to be x minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus a bunch of other terms. Okay. But we've seen this before. We've seen 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, so on before. This whole mess here is the same thing as the cosine. Okay, if you've forgotten, go back and look at the notes for the cosine function, and that's what you should get. And this whole mess right here is the same thing as the sine function. Okay. So the conclusion that we take away from this is something quite profound, that e to the ix is equal to cosine of x, that's this first part here, plus I times sine to the x. Sine of x, I'm sorry. Cosine of x plus I times sine of x. Okay. And this is quite a beautiful result. And then let's look at for a special case. Okay, so let's see what we have when we get e to the I pi. In other words, we put in pi for x. Well, that's going to be equal to the cosine of pi plus I times the sine of pi. So e to the I pi then is equal to cosine of pi is just 1 and sine of pi is just 0. So we can rearrange this a little bit and say that e to the I pi minus 1 equals 0. And this is otherwise known as Euler's formula. And we have to be careful because Euler was so prolific that, like, everything is named after him. But this is considered the most beautiful formula possible. And notice how interesting it is. It includes e, pi, an imaginary number, and then the common numbers that we're well known with, which is 0 and 1. Okay, so this says something kind of crazy, that if you had like the base e and you raised it to an imaginary number in the exponent, you would get the same thing as cosine x plus sine x times that number. Thank you for watching. Have a wonderful day. Be sure to watch just one more video that discusses the historical aspects of this.